Knowledge 2, here is your video for lesson 7.5 in operations with radical expressions. So we've looked at a lot of these simplification techniques already, but it never hurts to keep practicing these and to keep getting better. I personally really enjoy these because once you've done about 3 or 4, you start to see the patterns and it gets a lot easier. So there's a quick concept summary up here. I'm not going to go over it because this is a lot of math language. You can definitely read it, dig into it if you want, but I think it's easiest if we just jump right into the actual work of it. So to start off, we're going to start off by simplifying. We're going to break down roots. And the easiest way to do this is by breaking each number or variable inside down into its smallest factors. So with 27, I'm going to do a little factor tree, but instead of doing a factor tree the normal way, I'm going to factor tree all in one long radical sign. So 27 breaks down into 3 times 3 times 3. 3 times 3 is 9, 9 times 3 is 27. And because this is a square root, we are essentially looking for any hidden squares inside of the radical. Any hidden squares basically means anything that comes in pairs. So in this case, when there is a pair inside, we are unsquaring that. We can take that out and put it on the outside of the radical as just a single, because essentially that square root unsquares what is inside. From there, if there's no other pairs for us, we're going to leave the rest of the radical alone. Again, this is probably review, but I always like to go over it again just to make sure that we're all on the same page. This one is very similar, however, you see a number outside. Well, when that number is outside, it just means whatever we pull out of the radical is going to be multiplied by a factor of 5. So let's see what that looks like. 54 can be broken down into 6 and 9, and then 2, 3, 3, 3. Again, this is a square root, even though the 2 isn't there in our picture. And I'm looking for the pairs. So I pull a pair of 3's out. When I pull it out, it becomes unsquared, and it's just a 3 on the outside. This is the same thing as saying 5 times 3 times the radical of 2 times 3. We never want to leave it this way, though. We always want to simplify both outside and inside the radical. So I'm going to simplify the outside to 15 and simplify the inside to 6. That's that one. The last one, very similar. This time, instead of looking for squares and pairs, we're looking for cubes and trios. So when I break this one down, 24 can be broken down into 3 and 8, which is the same thing as 2 times 2 times 2 times 3. Now this number on the outside tells me what I'm looking for. So I look for a set of 3 numbers or of a variable if you have one in there. And that is what comes to the outside. Uncube that, we just get 1. Notice, I only took one set of 3 out, so only one number, 1, 2, ends up on the outside. You don't take 3 out. You are uncubing 2 cubed, which just results in a 2. Just that simple. Let's take that a step further and combine like roots. Now, these don't look like roots, but we have to simplify them first. I personally, when I'm working with any type of radicals or square roots, I like to simplify them furthest and then do my other operations. So in this case, 4 times the square root of 3, not really anything we can simplify. However, 5 root 12 is something that I can simplify, because 12 is the same thing as 2 times 2 times 3. I'm going to bring that pair of 2's out and multiply it by my 5 to be 10 root whatever is left over. In this case, it's 3. So 5 root 12 and 10 root 3 are the equivalents. And then, notice those are now like roots, but the 7 times the square root of 27 is not. So I'm also going to simplify that one. That becomes 7 root 3 times 3 times 3. I pull a pair of 3's out, it becomes 1. So this is the same thing as 21 root 3. Now when I rewrite this, I can rewrite it as the like roots. I've got 4 square root 3 plus 10 square root 3 minus 21 square root 3. And a lot of people get confused by all of the radicals going on here, but the way that I like to think about this, and one of the ways that I thought about it in college, was something called substitution. Instead of working with this idea of a square root of 3, I would replace that with an x in my problem. So that would look something like this: 4x plus 10x minus 21x. This would allow me to see only the coefficients instead of being confused by the coefficients and the radicals. Now I can do some simple math. 4 plus 10 minus 21 is negative 7x. But the same way that I substituted the square root of 3 for x, I can now go the opposite direction. So this is not my final answer. I have to substitute it back in as negative 7 root 3. And that is my final answer. If any of you are going on to college in the next couple years, this is going to be a really big trick that they show you, especially in the higher calculuses. You may even see it in AP Calculus. All right, let's move on. Next up is rationalizing the denominator. Not a super hard skill, not super challenging, but you have to be careful. And here's why. Essentially, we've got a ton going on, and I'm still going to follow what I set up here, where I prefer to simplify and then take my other operations. So let's start with that, and then we'll get into the challenging stuff. I'm going to simplify 5 root 48 into 5 root, this would be 2 times 2 is 4, 48 divided by 4 is 12, so then this would be 2 times 2 times 3. So 5 root there. I'm looking for squares or pairs, so I pull out one set and a second set. That's the same thing as pulling out 2 times 2, so 5 times 2 is 10, 10 times 2 is 20, so that's equivalent to 20 root 3. Let's simplify that root 75. That becomes 3 times 5 times 5. My pair is 5. There's nothing outside, so I'm just going to put it outside, and I'm actually going to bring it down here if you can follow all my arrows. So plus 5 root 3 all over 5 root 2. Now there's a ton of methods to do this. You can simplify these and reduce them. You can add the top and then rationalize. You can rationalize now. I'm going to do what makes the most sense to me, which is just simplifying the top. I've got 20 root 3 plus 5 root 3. That's just 25 root 3, as we saw in our last problem. And it's over 5 root 2. Again, I can rationalize at this point as well, but I want to slow my roll. I want to do things as simple as possible, so I'm going to continue to just simplify. 25 over 5 is just 5. So I can rewrite this as 5 root 3 over root 2. That's just simple fraction work. All right, last thing. This is where the actual rationalizing comes in. We are going to take this square root on the bottom. We don't like the square root on the bottom. And what we're going to do is we're going to multiply the bottom by that exact same root. But whatever you do to the bottom, you have to do to the top to keep it balanced. And why are we allowed to do this? Well, you'll notice anything divided by itself is just 1. So all I've done here is multiply by a big fancy 1 in order to make the problem look a little bit nicer. I've talked about this before in some of my past videos. So now we simplify the same way we would. Remember, we always multiply the outside times the outside and the inside times the inside, and we can only multiply radicals that are the exact same. So because these are both square roots, I can multiply the inside stuff. So 5 root 6 over square root 2 times square root 2. Anytime you multiply things that are the exact same like that, we get 2. We just get the number that is inside because those essentially cancel each other out. From here, I can't simplify this any further, so this is my final answer. What I want you to notice about this problem before I move on, there's a lot more simplification than there is rationalizing. The majority of your radical problems are going to be simplifying them rather than actually rationalizing. So this was the first type of rationalizing that we're going to do, and that's when you only have one term on the bottom. You'll notice with the next one, we have 2 terms on the bottom. We have a 6 and we have a 5 root 2. If you remember from some of our past work in class, this is where we are going to multiply by the opposite, essentially. So this one, because I can't simplify it at all first, I have to jump right to let me get a hold of my words here. Instead of simplifying, I have to jump directly to rationalizing. So I'm going to start by multiplying the bottom by 6 minus 5 root 2. Remember that from earlier in the year. By doing this, we are essentially canceling out our root. We can't just multiply by the root as we did in this last one, because then we end up with a ton more on the bottom to deal with, and we want to keep simplifying, not making the problem harder. But again, whatever you do to the bottom, you must do to the top. 6 minus 5 root 2. I like to put it in parentheses just because it's a cohesive idea for me. And then we have to FOIL to simplify. So I'm going to bring all of my foiling stuff down here. So 6 times 1 is 6. 1 times 5 root 2 is negative 5 root 2. Negative root 2 times 6 is negative 6 root 2. Remember, I can only multiply things on the outside, so negative 1 times 6 becomes negative 6. Root 2 times no root is just that root 2. And then negative root 2 times negative 5 root 2. That's the same thing as negative 1 times negative 5, which is positive 5. And root 2 times root 2, which is 2. Notice there's a multiplication going on there. We're going to have to simplify that in just a minute. But let's simplify the bottom first. 6 times 6, 36. 6 times negative 5 root 2 is going to be negative 30 root 2. Positive 5 root 2 times 6 is positive 30 root 2. And then positive 5 root 2, negative 5 root 2. 5 times negative 5 is negative 25. Root 2 times root 2 is 2. Again, multiplication going on there. Let's jump up here. I'm going to simplify the top. This 5 times 2 becomes 10, so I essentially have 6 plus 10, which is 16. Negative 5 root 2, negative 6 root 2. Combining those like roots to be negative 11 root 2. All over. Notice the reason that we multiplied by the negative version of what was on the bottom was this. These two terms now cancel each other out, and we are left with no radicals on the bottom of our fraction, which is exactly what we wanted. I have to multiply over here. I've got negative 25 times 2, which is negative 50. So 36 minus 50 is going to be negative 14. This is as simple as we can get because we can't reduce anything. We don't have any radicals on the bottom, and our radical up top is as simple as it can get. So that is our second type of rationalizing. So if I were you, I would go ahead over in the margin here, maybe make yourself a little bubble, a little note that says when there's only one radical on the bottom, you multiply by that radical in order to rationalize. When there is two terms on the bottom, you have to multiply by the negative version that opposite. There's a term for this. I feel really bad as a math teacher right now because I can't think of what it is. But if I think of it by the end of the video, I will let you know. All right, let's jump to the back. One of the last things we're going to learn here is roots with variables and products. However, this is the exact same as just numbers. Now we're taking into account letters. We're pretty solid with variables at this point in Algebra 2. So for this first one, I'm going to do the same thing that I did with the last page. I'm still going to write it out in the long version of the radical. I know that 32 is the same thing as 2 to the 5th. I'm not going to write out all those 2's. It takes a long time. Same thing with the 8 and the U4 and V5. But what I am going to do instead is I'm going to write these out in terms of things that can be uncubed or taken the cubed root of. For example, x to the third could be taken as an x. X to the third could be taken as an x. Once I've taken those two out, I'm left with x squared. So essentially all I've done is I've taken this x to the 8 and I've broken it up into 3 separate terms. And what that allows me to do is see that I have a trio here that I'm going to pull out. I have a trio here that I'm going to pull out, and those are just going to become x's on the outside of my radical. Same thing with my u and my v. U will end up being u to the 3u. V will end up being v to the 3v squared. And I can pull out anything with an exponent of 3. And I can do the same thing with this 2 to the 5. So now I'm going to do that. I'm going to pull out 3 of those to be 2. I already said anything that has an exponent of 3, I'm going to pull 1 out. So x and x, there's 2 of those. X squared. Pull out that u, the v, and then left over in the radical is anything that I didn't address. So there were, if I took 3 of these, there were 2 left over, so 2 squared is 4. I'm left with x squared, a u, and a v squared, which cannot be simplified because I'm taking the cubed root instead of the square root. So it's really important to recognize what root you're actually working with. And then, of course, there's no other perfect cubes inside that I can pull out to the front, so that is my final answer. Now, that's the long way of doing it. In my head, all I think of is how many times can this number go into the big number. How many times that is, that's how many you're pulling out. So 3 goes into 8 nicely 2 times. The remainder of that, 8 divided by 3, is 2 remainder 2. That remainder is what is left inside. Again, however you want to think about it, totally fine with me. Let's see another one here then. Remember what we've been talking about this entire time as well as in the last video. We're okay with negatives in the radical as long as the radical is odd. In this case, it's a cubed root. So let's write this out. Negative 27 is the same thing as negative 3 cubed. And then that x seventh, I'm going to use my remainder theorem here instead of rewriting it. So the cube, those two cancel out in that case. So the negative 3 comes outside. And now I'm going to look at this and say, I know that x to the 7th and that cube, 3 will go into 7 2 nice times. So I have x squared. When I do that, I have a remainder of 1x, and that is what stays inside the radical. There's some really awesome theory behind this, and I would encourage you to check it out if it's something you're interested in. Come chat with me. However, this is the easiest way that I have found to think of simplifying any roots with variables and products. All right, last one in this section. So this one, we've got 6 times the cubed root of 9n squared times 3 times the cubed root of 24n. Remember what I said last time, we only multiply things on the outside and we only multiply things on the inside as long as the radicals are the same. So I'm going to start off right away. Let's just simplify the outsides. 6 times 3 is 18. Boom, we've already simplified something. Take those little victories, you know? And then I'm not going to multiply these because I know what I'm eventually going to do is break them down into their smaller parts anyway. So what I'm going to do is if I'm multiplying, I'm going to bring those together, but I'm going to break them down all in one large radical. So for example, this 9n squared is the same thing as 3 times 3 times n. And because I'm multiplying it times 24, I'm going to multiply it by 3 times 2 times 2 times 2 times n. That way I've multiplied it, but I've also taken that opportunity to break it down. I don't need to multiply these together, put them together, and then break them down. It's a lot of extra work. We don't want to do that. From this point, I'm looking for nice trios, nice cubes. So anything that comes in threes, I'm going to pull out to the front. In this case, they're not together, but I've got threes, I've got a set of twos, and I've even got n's. That takes care of everything in my cube root, so I'm going to bring those out to the front. 18 times, we talked about the threes, the set of twos, and the n. And if there's nothing left over in the radical, I don't need to add it. Let's simplify that one step further. 18 times 3 times 2 times n is the same thing as 108n. And that's my answer for that one. I think these problems are really cool. Maybe this is just the nerd in me, that we can go from something that looks like this, with all these numbers, with all these radical signs, down to a really nice expression that has none of that. It's just cool stuff. All right, that was products. These are quotients. We've already worked with this. Let's check it out. Remember, when you've got the square root of a fraction, we can split that square root up over the numerator and the denominator. And from there, we are simplifying them separately. What is the square root of x to the 4th? Well, how many times does 2 go into 4 nicely? Twice. So I have x squared on the top. And you can check that with the longer methods that we've been working with up here if you'd like to. The bottom's a little bit trickier because we only have one nice y, and we're left with the square root of y on the bottom. Now, while there's nothing technically wrong with this answer, it is correct, it is not rationalized. So essentially, you have not simplified it completely. In order to rationalize, we've only got one radical on the bottom. There's no addition or subtraction. So we're going to multiply by that radical only. Y times y, in this case, in the square root is y. So you're left with y squared on the bottom. You've got x squared times the square root of y. So you've got that left on top. I know this doesn't look any nicer than this, but it is technically the correct answer because it is fully simplified. If you are watching this video right now, I want you to send me an email for bonus points. I'll give you a few bonus points. If you can remember and tell me from earlier in the semester why we have to rationalize the radical out of the denominator. Let's see who was listening in class earlier. All right, next one. This one we've got the 5th root. Same thing, the same way that we split up a square root, we're going to split up that 5th root. We're going to give it to the top. We're going to give it to the bottom. And from there, we can't simplify anything, but we still have to rationalize it. So